Welcome to Conic Sections, Constructing the Hyperbola. We start with a verbal definition of a hyperbola. We use that to graph a hyperbola, and then based on the definition and the graph, we derive the equation of a hyperbola. A hyperbola has two foci are points, and a constant distance, which will be represented here by the length of a black ribbon. The distance between a point on the hyperbola and one focus minus the distance between the same point on the hyperbola and the other focus equals that constant represented by the length of a black ribbon. You may recognize this definition. It is almost exactly the same definition we used for the ellipse. The only difference is, with the ellipse, the two distances added to equal the constant. With the hyperbola, you subtract the distances to get the constant. Because the verbal definition is so similar, the equations also are very similar. The only difference in the definition is a plus versus a minus, and so the only difference in the equation is again a plus versus a minus, adding versus subtracting. But that makes a huge difference in the graph. The graph of a hyperbola does not look at all like the graph of an ellipse. We have two foci here, points. I'm going to call them F1 and F2, and I have a blue ribbon which I'm going to use to find points that are all the same distance away from focus 1. They're all the length of the blue ribbon away. Then I attach to that blue ribbon a black ribbon, so the total distance is longer now, and I find points that are that distance away from the other focus. Where those arcs intersect, I get a point. There are two of these, one near the top of the graph and one near the bottom. If we look at where we got this point, its distance from focus 2 is the blue ribbon plus the black ribbon. Its distance from focus 1 is just the blue ribbon. So if you take distance 2, the distance away from focus 2, and you subtract distance 1, the distance away from focus 1, you're taking the blue and black and subtracting out the blue, so you're left with the length of the black ribbon. We do this again with a different color ribbon, green this time. The green one's a little shorter than the blue one, so I get points that are a little closer to focus 1. Then I combine the green ribbon with the black ribbon, the same black ribbon as before, and I find points that are that distance away from focus 2. Where those arcs intersect, I have more points for my hyperbola, one near the top of the graph and one near the bottom. Once again, let's look at one of these points and think about its distances. The distance from focus 2 has two parts, the green ribbon plus the black ribbon. The distance from focus 1 just has the green ribbon. So if you take the longer distance, the green and the black, subtract the shorter distance, the green, you're left with only the black. Distance 2 minus distance 1 equals the length of the black ribbon again. All the points we find on the hyperbola will follow this same relationship. Here we do it again with an orange ribbon. The orange is a little shorter than the green, so we get points a little closer to the foci. Again, the distance from one of these orange points to the further focus, focus 2, is the orange plus the black. If we subtract the shorter distance, which is just the orange ribbon, we'll be left with that black ribbon again. The difference is always equal to the length of the black ribbon. We do it again with a shorter ribbon. This one's red, and one shorter than that. This one's fuchsia. And finally, we get down to a very short ribbon indeed, the purple one. From focus 1, I go out the length of the purple ribbon. Then from focus 2, I go out the length of the purple ribbon plus the black, and it just barely meets. I don't have 2 points where the arcs overlap anymore. I just have one on the line between the two foci. This point is called a vertex. I'll call it V1 for vertex 1. We will have vertex 2 a little later. Now we run a curve through all of these points, and this curve is one branch of the hyperbola. We can do all the same things again, but now finding points that are closer to focus 2 and further away from focus 1. Here's the blue ribbon back again, just the blue ribbon from focus 2, the blue ribbon plus the black ribbon from focus 1, and where those arcs intersect, we get points. We can do this again with the green ribbon, the orange ribbon, the red ribbon, the magenta ribbon, and finally the purple ribbon that gives us the other vertex. I told you there would be one. This is vertex V2. We run a curve through all of these points, and that is the other branch of the hyperbola. Next, we add a coordinate system to our hyperbola. The x-axis runs through the foci and the vertices. The y-axis is perpendicular to the x-axis and runs right through the middle of the hyperbola, exactly midway between the two foci. The distance from the center to one vertex is called a. This allows us to give coordinates to the vertices. The one on the right is a0. The one on the left is negative a0. The distance from the center to one focus is called c. The one on the right is c0, and the one on the left is negative c0. Now I'm going to take the distance c, which is about 8.5 centimeters, and run that same distance from a vertex to the y-axis, however far up the y-axis we have to go, so that we have 8.5 centimeters from the vertex to the axis. This creates a triangle with a vertical side I'm going to call B. The top of this triangle has coordinates b0, and there's a similar point b spaces down from the center with coordinates negative b0. We made a triangle like this in the ellipse, and that point b spaces up was a vertex of the ellipse. But here in the hyperbola, that point doesn't seem to have anything to do with the hyperbola. It doesn't touch the hyperbola, it's just some point on the y-axis. But it's actually more useful than it looks. I'm going to draw a horizontal line through that point b spaces up at the top of that triangle, and another horizontal line b spaces down from the center, and vertical lines through the vertices. This creates a box, and I'm going to draw diagonal lines through the corners of the box. The reason we need the box is to find the corners, so we can put these lines in the right places. These diagonal lines are asymptotes of the hyperbola. The further out the hyperbola goes from its vertex, the closer it gets to one of these asymptotes. It never touches the asymptote, but it gets closer to the asymptote as it goes further out. If you're trying to draw a hyperbola, it can be quite helpful to know where the asymptotes are. That can save you a lot of trouble with colored ribbon and plotting points. So we're going to need to be able to find the value of b to know how far up the y-axis to go to draw this box. Well, we see we have a right triangle here with legs a and b and a hypotenuse of c. So it has the Pythagorean relationship a squared plus b squared equals c squared. We had a relationship like this with the ellipse, but in the ellipse it was a little confusing because the longest side was actually a and we're accustomed to it being c. In the hyperbola we're back to what we're used to. The longest side is c, so a squared plus b squared equals c squared. We can find any point on the hyperbola xy, find the distance to the focus that is farther away, and subtract the distance from that same point to the focus that's closer, and we always get the length of the black ribbon. The length of the black ribbon is an important part of the definition here. Although in math textbooks they don't talk about black ribbons, they relate it to the A and the B and the C. So let's get the ribbon back out again, particularly the purple one. If I run the purple ribbon from focus 1, I get to vertex 1, and from the other focus, the longer distance, I ought to have the purple ribbon plus the black. So with these two purple ribbons here, each going from a focus to a vertex, we see that the black ribbon is suspended in between. It just runs from one vertex to the other. The distance from the center to one vertex we've already named A. The distance from one vertex through the center out to the other vertex is then 2A, so the length of the black ribbon is 2A. That makes our definition for points on the hyperbola. If we take distance 2, the distance from our point to the further focus, and subtract distance 1, the distance from our point to the closer focus, we get 2A. 2A is exactly the distance between the two vertices. Now we take the coordinates from our sketch at the right and apply them to the verbal description of the hyperbola, which is given at left. A hyperbola has two foci, points, and we see these have coordinates c0 and negative c0, and a constant distance, the length of the black ribbon, which is 2A. Then we want the distance between a point on the hyperbola and one focus. The point on the hyperbola has coordinates x, y, and the first focus has coordinates c0. For the distance formula, we want the square root of the sum of the squares, the difference in the x-coordinates squared, plus the difference in the y-coordinates squared, minus the distance between the same point, xy, and the other focus, negative c0. So that's a similar distance formula, only we have x minus negative c instead of x minus c. And this equals the constant, the length of the black ribbon, which is 2A. From this we can write an equation. That radical that is the first distance minus the radical that is the second distance equals 2a. Well, maybe it equals 2a. If we take the larger and subtract the smaller, we get 2a. But what if this is the smaller subtract the larger? How do we know which one's larger? Well, if the order of the subtraction is backwards, we'll get negative 2a instead of positive 2a. So to cover all of our bases here, I'm just going to write plus or minus on the 2a. We'll deal with the plus or minus as we go along. To solve this equation, we need one radical alone on one side of the equal sign. So I'm going to add that second radical to both sides. Then we square both sides. On the left, we're just squaring a square root. That cleans up nicely. On the right, we're squaring a binomial. So we need the first term squared. The first term is the plus or minus 2a. When we square it, it's going to be positive, and we get 4a squared. Then 2 times the first times the last. 2 times the plus or minus 2a times the radical. And finally, the last term squared. When we square the square root, we just get what was under the radical. This gives us a y squared on both sides of the equal sign. We can subtract that out. And then we multiply out the squares. X minus c squared on the left side, and then on the right side, x plus c squared. This gives us some more things we can subtract out. We can subtract x squared from both sides. We can subtract c squared from both sides. We have 2cx on both sides, but we can't cancel that out. On one side it's negative, and on the other side it's positive. So we add 2cx to both sides to bring those pieces together. This leaves us with 0 equals 4a squared plus or minus 4a times the square root of the quantity x plus c quantity squared plus y squared plus 4cx. There's a lot of 4's and a's in there. I'm going to divide everything all the way through by 4a. This cancels out the 4a on the radical and leaves it just plus or minus the radical. I'm going to move that to the left-hand side to get it alone. So we have plus or minus the square root of x plus c quantity squared plus y squared equals a plus c over a times x. Now we square both sides. On the left side, that gets rid of the plus and minus and gets rid of the radical. And on the right side, we have to multiply out a binomial again. Square the first, that's a squared. 2 times the first times the last, the a's cancel and leave us with 2cx. And then finally the last term squared, c squared over a squared times x squared. Then I multiply out the square, the x plus c quantity squared, and that gives us a 2cx on the left as well as a 2cx on the right. We subtract those out, and then in the next step, I want everything involving x or y on the left and everything not involving x or y on the right. So the x squared stays where it is, and then I subtract c squared over a squared times x squared from both sides. The y squared stays where it is, and I subtract c squared from both sides. I would like for the two pieces involving x squared to have a common denominator. So I multiply that first x squared by 1, writing 1 as a squared over itself. Now I can factor x squared over a squared out of those first two terms, leaving behind a squared minus c squared. I'm out of space here, so I'm going to move on to the next page, bringing that exact same equation to the top of the next page. X squared over a squared times the quantity a squared minus c squared plus y squared equals a squared minus c squared. We have a squared minus c squared in two places. I'm going to divide all the way through by that, and that leaves us x squared over a squared plus y squared over a squared minus c squared equals 1. Now that a squared minus c squared looks very familiar. In the ellipse equation, that was equal to b squared. But this is a hyperbola, and in the hyperbola, c is larger than a, so that a squared minus c squared in that denominator is negative. We factor a negative out of it, making that denominator negative of the quantity c squared minus a squared. C squared minus a squared in the hyperbola is b squared. So here we're using the Pythagorean relationship we talked about earlier. A squared plus b squared equals c squared, so b squared equals c squared minus a squared. And that's the last step needed to put our equation in standard form for a hyperbola. We can compare it to the ellipse equation, x squared over a squared plus y squared over b squared equals 1, and we see the only difference here is the sign, the minus or the plus. That's what we would expect because, in the verbal definition, the only difference in those words, besides changing the name from ellipse to hyperbola, was changing a word from plus to minus, and that's the effect it has on the equation. These equations look very similar, but they make very different shapes. So when we're graphing them, we do have to pay attention to whether we have an addition or a subtraction. To draw a hyperbola, we will start by finding the central rectangle. Lines drawn through the center and corners of this rectangle form asymptotes for the hyperbola. The vertices of the hyperbola are at the centers of opposite sides of the central rectangle. The hyperbola touches the central rectangle only at the vertices. From these vertices, the hyperbola curves out to approach the asymptotes. The two vertices of the hyperbola are connected by the major axis. The distance from the center to one vertex was called A, so the length of the major axis is 2A, which was the length of the black ribbon. The minor axis connects the two ends of the central rectangle that are not touched by the hyperbola. The distance from the center to one end of the minor axis is called B, so the length of the minor axis is 2B. The points at the ends of the minor axis are sometimes called the co-vertices. As with the ellipse, the length of the major axis is 2A, and the length of the minor axis is 2B. But unlike the ellipse, there is no rule for which one is longer. The major axis could be longer or shorter than the minor axis. If the two axes are the same length, the hyperbola is called a rectangular hyperbola. The major axis always connects the vertices, which are on the hyperbola. The minor axis always connects the co-vertices, which are not on the hyperbola. We can form a right triangle by drawing a segment connecting a vertex with a co-vertex. The length of this segment is called C. This is also the distance from the center to a focus. The hyperbola that I drew with the pins and ribbons had a horizontal major axis, like the one sketched here. As we have just seen, the variables x and y appear in squares. The denominator under the x squared is a squared, because a is the distance from the center horizontally to the side of the central rectangle. The denominator under the y square is b squared, because b is the distance from the center vertically to the top or bottom of the central rectangle. The subtraction is a key element of the hyperbola equation. When you see addition here, the graph is an ellipse. It is also possible to draw a hyperbola with a vertical major axis. We start with the same central rectangle and asymptotes, but we draw the hyperbola with vertices on the top and bottom of the box rather than on the sides. Whether it is horizontal or vertical, the major axis always connects the two vertices. Its length is always 2A, so the distance from the center to one vertex is still A. The distance from the center to a co-vertex at the end of the minor axis is still called B. The segment connecting a vertex with a co-vertex still has length C. C is also the distance from the center to one focus. The foci are always on the major axis, whether it is horizontal or vertical. The equation is similar to the previous one. We could derive it in the same way, but this video is long enough already. Again, the variables x and y appear in squares. The denominator under the y squared is a squared, because a is the distance from the center vertically to the top or bottom of the central rectangle. The denominator under the x squared is b squared, because b is the distance from the center horizontally to the side of the central rectangle. The subtraction is a key element of the hyperbola equation, but this time the order is reversed. When the major axis is vertical, the y squared term is the positive one, and the x squared term is subtracted from it. These equations all put the center of the ellipse at the origin, where x and y are both 0. To put the center at another point, with coordinates hk, we replace each x with x minus h, and replace each y with y minus k. The denominators are the same as before. The one under the x squared term always tells how far the central rectangle goes to the left and right of the center, and the one under the y squared term always tells how far the central rectangle goes above and below the center. The one that is positive corresponds to the major axis, which has both the vertices and the foci. The one that is subtracted corresponds with the minor axis. In the next video, we will use these equations to graph some hyperbolas.